Solids differ from the other states of matter in that they have long-range order. To achieve long-range order, all the constituent particles need to be arranged in a symmetrical pattern in 3 dimensions. We will extend our knowledge of close packing in 2 dimensions to build symmetrical patterns in 3 dimensions. Let's first study 3-dimensional close packing from 2-dimensional square close packing. In order to build a 3-dimensional structure, it is easier to stack 2-dimensional square close-packed planes one above the other. As you can see, the spheres are aligned horizontally as well as vertically. If the arrangement of spheres in the first layer is considered to be of A-type, then the arrangement of spheres in the subsequent layers is also of A-type. This 3-dimensional arrangement is referred to as AAA-type packing. If you look carefully, you will find that this arrangement has resulted in the formation of a simple cubic lattice. The unit cell of this lattice is a primitive cubic unit cell. Another way to build a 3-dimensional close packing is from a 2-dimensional hexagonal close packing. As you can see, the depressions of the first layer are the ideal seats for the next layer of spheres. By placing the constituent particles or the spheres in the depressions of the first layer, a second plane of closed packed spheres lying on the first plane is generated. It is important to note that when the spheres are placed on the voids of B-type in the first layer, the C-type voids are left unoccupied as no sphere can be placed in them. As the spheres of the 2 layers are aligned differently, let the arrangement of spheres in the first layer be referred to as A-type and in the second layer as B-type. A closer look at the arrangement indicates the formation of 2 different kinds of voids, marked as O and T. If you look carefully, you will find that this arrangement has resulted in the formation of a simple cubic lattice. The unit cell of this lattice is a primitive cubic unit cell. It is also called cubic close packing, CCP, or face-centered close packing, FCC. Further, as can be seen in hexagonal close packing and cubic close packing, a sphere has the coordination number 12. It is in contact with 6 spheres in its own layer, 3 more in the layer above, and 3 more in the layer below. Also, both the forms hexagonal close packing and cubic close packing are equally efficient in terms of filling up space. In both of them, 74% of the space in the crystal is filled up. Let us now look at the number of tetrahedral and octahedral voids present in these arrangements. In a close-packed structure, whether CCP or 8CP, if there are n spheres in the packing per unit cell, then the number of octahedral voids is the same as n, while the number of tetrahedral voids is equal to 2n. For example, in a CCP arrangement, if 4 atoms or ions are present per unit cell, then the number of octahedral voids is also 4, while the number of tetrahedral voids is 8.